Bismillah ar-Rahman ar-Rahim. We are still in chapter 4 of Strang, talking about projections using orthogonal basis. Q replaces A. Remember that projections are connected with matrices with more equations than unknowns, that is m greater than n. When the columns of A are a basis for the subspace, A is m by n, and n is less than m, the column space of A, C of A, is a subspace of Rm, and it has dimension n equal to the rank of A. The projection onto C of A of a vector B is P equal to projection matrix P times vector B, where P equals A times A transpose A inverse times A transpose. When the columns of A are orthogonal, that is A goes to Q, then P is Q times Q transpose Q inverse Q transpose, which is Q times I Q transpose, which is Q transpose equals I, which is m by m. Okay, we have n separate one-dimensional projections. P equals Q times x hat. Written in matrix form is P equal to Q1, Q2, Qn times Q1 transpose B up to Qn transpose B, which is the decomposition of B into the subspace with Q1 and Q1 transpose B plus Qn transpose B. As an example, project B, which is 0, 0, 1, onto the column space of the orthogonal matrix Q. Okay, the columns are orthonormal, that is, they are orthogonal unit vectors. The projections here are P1, Q1 to Q1 transpose B equal to 1 over 3 times minus 1 to 2 times the first column transpose times B, which is 2 over 3 times Q1. The same is for Q2, okay, and for Q3, projections on Q1, Q2, and Q3. If we add the three projections, P1 plus P2 plus P3, we come up with the vector B again. Now we come to the Gram-Schmidt process. Since projections are simple when we have orthonormal columns, the question arises that if the columns of A are independent, how can we obtain an orthonormal basis instead of the columns of A? This is the Gram-Schmidt process. Gram-Schmidt, suppose A is the vector A1, vector B, the vector A, vector B, vector C. Okay. We want to find three orthogonal vectors, A, B, C, capital A, capital B, capital C, instead of A, B, C. Then divide A, B, C by their lengths to get the unit vectors Q1, Q2, Q3, which are orthonormal. We begin by choosing A equals small a. The next direction B must be perpendicular to A, so start with B and subtract its projection along A, as you see in this figure. Okay. The projection of B onto A is P, small p, okay, and B is the error vector. So B is small b minus the projection A transpose B onto A divided by A transpose A's. Okay. We can check orthogonality. A transpose B, capital A transpose times capital B, is A transpose B minus A transpose A divided by A transpose A times A transpose B, which is equal to 0. B is what we call the error vector E, which is perpendicular to A. We now have two perpendicular directions, A and B. The third direction, C, is the error vector when C is projected onto the plane formed by capital A and capital B. So capital C is small c minus the projections onto capital A and capital B. The last step is to find Q1, Q2, and Q3. So the best thing is to take an example. Suppose A is the 1 minus 1, 0, B 2, 0 minus 2, and C is 3 minus 3, 3. These vectors are independent because Ax equals 0 has only one solution, x equal to 0. Check by Gaussian elimination. If we carry out Gaussian elimination, okay, to reduce A into U, so we see that we have 3 non-zero pivots, and so the rank of the matrix is 3, and the only solution of Ux equals 0 is x equals 0. So now we applied Gram-Schmidt, okay, to this matrix A. We take A, capital A equal to small a, then capital B is B minus the projection onto A. So we get this. We check that A transpose B equals 0. So it is 0. Now subtract the two projections from C to find capital C. So it is capital C is small c minus the projection onto A, capital A, and the projection onto capital B. If we add them up, we get this vector. Now check that A transpose C equals 0 and B transpose C equals 0. So they check. The lengths of A, B, C are root 2, root 6, and root 3. If we divide by those, we get the orthonormal basis, Q1, okay, and Q2 and Q3. So this gives us the matrix Q if we combine these three columns. Okay, now the Q factorization of A. How are Q and A related? Okay, we know that the vectors A, small a, and capital A, and Q1, the unit vector, are all along a single line. The vectors A, B, and capital A, capital B, and Q1, Q2 are all in the same plane. The vectors A, B, C, and A, B, C, and Q1, Q2, Q3 are in one subspace of dimension 3. To find the relationship between Q and A, okay, we go back to the previous equations for capital A, capital B, capital C, okay, and we can solve for small a, small b, small c as follows. Okay, so capital A equals small a, written in terms of the unit vector Q1, so it is Q1 times the projection of A onto Q1. Then from the other equation for capital B, we solve for small b. Okay, so we come up with the projection of B onto Q1, then capital B is really the projection of B onto Q2. So this is the equation for B. Similarly for C, capital C, we can solve for small c, and we can see it is the projection of small c onto Q1, Q2, and Q3. Okay. The last three equations may be written in matrix form as follows. Okay, and we see that the matrix on the right is upper triangular, and this is called R, capital R, or we can write this equation as A equal to Q times capital R. R is upper triangular, and the advantage of QR factorization, okay, is the following. The least square solution using normal equations A transpose A times X hat equals A transpose B becomes, using the QR factorization, R transpose Q transpose times QR equals R transpose times B, R transpose times B, times B. So R transpose R times X hat equals R transpose Q transpose B is the normal equation. Or R times X hat equals Q transpose B. Since R is upper triangular, X hat is found by back substitution. This finishes chapter 4 of Strang.